Hi guys, Mr. McIntyre here, carrying on with our work on the circle and symmetry in the circle. Quick recap on what happens with chords and how chords meet diameters and or a radius. So we know that they meet at right angles, we know they bisect, we know that they can create triangles if we are to join the end of a chord to the center, like you see on the screen now. But what we're going to explore is this new term tangent, and what is a tangent and how do we create a tangent. So a tangent is just a line that touches the circumference at one point and one point only. So what we are going to be looking at is how we take this chord AB that you see me marking in green, and how we move that downwards or upwards to create a line that moves slightly outside the circle, just catches the circumference at one point that you see me highlighting in red. What that creates is a line EF, which is called a tangent. It touches the circumference at only one point, and we want to specifically look at what happens now if we join the end of this tangent to the center of the circle, and does that create the 90 degrees that we've had with chords. Right then, what is a tangent? A tangent is a line which even if extended would only touch a circle at one point. So we saw that in the previous slide. So effectively, if we're looking at this little diagram, only this red line could be considered a tangent because it touches the circumference at one point. I also just showed you how we take a chord, or in this case in the green line is a diameter, which is a special chord. If we were to drop that, then we would create multiple chords as we came lower and lower, and eventually would move outside of the circle. And what that would do is, we know from the previous work we've done that these are right angles. Now that does not change when we're dealing with the tangent. And what we want to do is see what actually happens there, because we know that when we join these lines, we create multiple right angle triangles, and the same would be true for the tangent. So as you can see here, if we take the line AB, imagine that's the green line we had dropped directly down. Okay, if we take that line and it's dropped and it creates a tangent on the bottom, the conditions that we had before where chords meet a radius or a diameter and they meet at right angles, they're all still true, because what effectively is happening is that chord drops down, goes outside a circle and becomes a tangent. Now what we do lose in that instance is we do lose the bisect the line condition. So it won't always bisect a tangent. We do know that it will cut in half, when it's inside and it's a chord. But for the rule on tangency, we're just going to focus on the 90 degrees, because that 90 degrees allows us to create this right angle triangle, as you can see on the diagram ABO. Okay, so what's actually happening is we've dropped the chord to the bottom. We've created the right angle triangle, but that can be done on both sides. Okay, now in this case, it looks like I'm drawing the tangent in the kind of even way, so it looks like it would bisect, but ultimately all we're looking for is the right angle. Now that can be true if we take the line from the center, no matter where the tangent is. If we had a tangent, if you look at the second circle, although the line's not absolutely perfect, if we were to take a line, whether it be a radius or a diameter, and have that meet the tangent, then the radius or the diameter would meet the tangent at right angles. It doesn't need to be something that is straight up and down like we've got on the screen. Okay, so again, if I was to take a tangent in the orange and join it with a radius, they would meet at right angles. And it's that condition that's going to dictate the next part. And obviously, naturally, we will move on to creating right angle triangles, and that leads to us using Pythagoras. Okay, let's go through an example. So First of all, let's try and identify a couple of elements to this circle. First, we've got a semicircle with centre 0. We've got a line OQ, which hopefully you'll recognise from the centre to the circumference is a radius. So that radius then meets the line PQ, which if we were to continue, well, is a tangent, but if we were to continue, maybe a little bit easier for you to see it as a tangent, based on the stuff we've just done. So that means a radius meets a tangent. And we know that, much like a chord, means that they meet at 90 degrees. So that effectively allows us to do is to extract this triangle, and you can redraw it however you like, but be careful when you're redrawing this. If it's easier for you to understand a right angle triangle like this, label your vertices carefully. So Q, the short side, it goes from Q to O. The long side goes from Q to the other short side goes from Q to P, and the longest side is P to O, and we know there's an A in the middle of that. So we have 3.6 and we have 4.8. So that means we can now calculate x, not x squared, which is the longest side. That's going to start us, and it did say, as a little hint in the question, find the length of PO first. So x squared equals 3.6 squared plus 4.8 squared. I've done this before, so I know that comes out as 36. X is therefore the square root of 36, which is 6 centimeters. So it is worthwhile recognizing that x is actually PO. So x is actually this distance along the bottom, PO. Now what I need to show you is this distance OA, which we can see, that's also a radius. Okay, it goes from O to the edge of the circle, the circumference, and therefore it's the same length as the first one that we mentioned, which is 3.6 centimeters. So actually, to calculate the distance PA, which is what we're ultimately being asked to do here, PA equals PO, that full distance, take away AO. So that's our 6 centimeters, which we calculated, and take away the 3.6 centimeters for the radius. So it's 2.4 centimeters long. Okay, where do we get the 6? The 6 comes from our Pythagoras, the longest side. Where did we get 3.6? That's the radius. Okay, a little example of how you would use a tangent, but mainly we're using the tangent to recognize a right angle triangle, which allows us to do the rest. Okay, there's something else that you will hear mentioned is the tangent kite, and what that refers to really, and I'll mark it out with a pointer, it's just two pairs or two tangents, PM and PN, that will approach a circle. They therefore create this kite shape when you put the radii in position. Now, this is a typical exam type question, and what we're asked for here is the area of a circle. So a couple of things to remind ourselves of. The area of a circle is pi r squared, and what that does is it makes it quite clear that we're going to need those radius values. Okay, so what we're actually being asked for here is discover the radius. Once we know the radius, we'll be able to find the area. Okay, so let's have a look at what we've got. We've got tangents, and therefore we have sets of our two right angle triangles. Now in this situation, it doesn't really matter whether we take the top one or the bottom one. Let's take the bottom one because it's a little easier to see the shape of it. So we've got a right angle triangle from O to M to P. Now you can see that we've got the hypotenuse is 39 centimeters, and based on the top triangle, the P to the N, which is the same size as P to M, obviously naturally with all the conditions of a kite, we can see that the shorter side on here is 36. So what we're really looking for, that ROM, is a shorter side using Pythagoras. So if we take, let's call it R just now, R squared equals 39 squared. So this time it's a subtract because it's a shorter side we're trying to find. So 39 squared, take away 36 squared gives you 225. So R squared equals 225. R is therefore the square root of 225, which we know is 15. So relatively simply now we have a radius that is 15. We want to find the area of the circle. So that's pi r squared. So pi times 225, because we know what that's r squared. So shift pi times 225 gives us 706.86 centimeters squared. Again, the use of a tangent to create a right angle, which gives us a right angle triangle, which allows us to deal with Pythagoras. And typically with an exam type question, there's another layer, so that takes us to our area of a circle. Okay, finally, just a quick look at a combination of some of the stuff we've done with semicircles and tangents. Hopefully, we'll start to recognize, and I'll use the pointer here. If we have this question here, and we would be asked to copy and complete or fill in all missing angles. Now, what I want you to do is to have a look at what we've got here. We've got technically 3 triangles. We have triangle 1, 2, and 3, but then actually an overarching 4th triangle that's surrounded in blue. So what we're looking for are any combinations of right angles that we can get. Okay, easiest one to look at is triangle 1. That's a triangle inside a semicircle. So we have, if we were to mark it, let's see, we'll call that PQR. We've got RQ is a diameter. The 2 shorter sides meet the ends of the diameter, and there's a point on the circumference. Therefore, that's 90 degrees. That allows us to find this angle in here. We want it to add up to 180. So we need that to be 29 degrees. That'll give us 29 plus 61 is our 90, plus the right angle, which is 180. So that one in there, 29 degrees. Second one we have QR is a diameter or a radius, and it's meeting, let's take this triangle as S, it's meeting RS, which hopefully you'll recognize as a tangent. So that means RQ and RS meet at right angles. So that would tell us that we can now get the shaded angle in green. We have 58, the right angle is 90. So this green angle up here gives us 32 degrees. Now the next part, how to finish that off, does get a little complex. So what I'll do is I will try and strip away some of the work in there and put in the size of the angles that we've done already. Okay, now that we've stripped back all the doodling over the top of this, we've got our 29 degrees, which we've discovered. We've got our 2 right angles, and we've got our 32. So the missing angles we have now are this inside here, this blue one, these red ones here, and we need to explore what's happened with some of the additional information we've got now that we've done some calculations. So I want you to have a quick look at RQ, and now we're looking at this point T. This is a point T that lies on the circumference. We've got RQ, we've already said, is a diameter. So actually, we can change the angle at T to 90 degrees. We're back into a situation where that's a second triangle inside a semicircle, and it's a right angle. And therefore, on the opposite side is also 90 degrees and a right angle at T. What that does, that allows us to get the green angle and allows us to get the blue angle. So we now have the green 32, so therefore we must have 58. That's 90, take away 32. And the blue one, 58, and therefore take away that from 90, and we've got 32 again. So actually, very simple calculations, but by inputting 4 different right angles, we can just use our angles inside a triangle, add up to 180 and find the missing angles. Now it is worthwhile saying that these green angle, the green and the blue angle there, we had already determined that the angle at R, which I'll put a circle in, was 90 degrees. So 32 and 58 would need to add up to 90 degrees for us to be absolutely sure that it's correct, and they do. So another little problem with multiple triangles, tangents, right angles, but all the rules that you've learned in first and second year should stand you in good stead.